Alright, so let's continue our review for the Unit 4 exam. And we've been talking about rotational concepts. It's getting hard to see me now because of all the formulas that are filling up this page here. But now let's talk about momentum. And so you don't need to know anything about what's in the green for the Unit 4 exam. You are going to need to know it for the final, though. But the concept of momentum, linear momentum, was given by lowercase p, and it was equal to mv. So it was mass in motion. Mass moving made momentum. So we can do the same thing for things that are rotating. And so we're going to say L is going to be angular momentum. This is linear momentum. This is angular momentum. And it's going to be, instead of mass, it's going to be the moment of inertia in motion. So this is going to be rotational motion. So you see how similar the two equations are. So this is for an object that is spinning like the Earth with a certain rotational speed. So the Earth is rotating once every 24 hours. Now that's not the right units, but that's its rotational speed. You could also have something that is orbiting. So in this case, a planet that is in orbit around a star. So let's draw a picture of it here. Here's the star, is going to be a certain distance away from it. So that's going to be r. And then the planet is going to have a certain mass, m. And then the planet is going to be moving in its orbit with a certain speed, v. So that we can put this all together, and we could say that it's going to be equal to the mass of the planet, its distance r, and then its speed. So this is going to be a spin, angular momentum, and then this one here is going to be orbital angular momentum. And what I want you to see is that if momentum is conserved, so conservation of momentum, then if you're an ice skater and you bring in your arms, then your R is getting smaller, so the V gets bigger in order to compensate, and you spin faster. In the case of a planet, if a planet gets closer to a star, the R gets smaller. And if the R gets smaller, the V gets bigger in order to compensate. So a planet speeds up the closer it gets to a star. And then as it moves away from the star, it starts to slow down again. That's what I want you to know for the exam. So you're not going to be taking any numbers and putting it into these formulas. I'm going to give you the formulas on the very first page of the exam. All you have to know is what are the letters, and then how do I use the formula in order to solve the question. So here's a sample question that might be on the exam about angular momentum. And here's another one. Oh, that definitely would not be on the exam. So you absolutely, positively do not need to calculate the spin angular momentum of the Earth. And then what's the orbital angular momentum of the Earth? Don't worry about that. I just went a little crazy, so I'm sorry about that. And then we've been assuming that there is no outside torque acting on the system. So remember, a torque is going to cause a system to accelerate. Well, another way of saying that is it's going to change the angular momentum of the system. So a torque changes the angular momentum of a system. If there is no torque, then the momentum doesn't change. And that's what we've just been doing right down here. Conservation of angular momentum. But if there is a torque, then something will precess. So we said that if there was no outside torque acting on the system, then something will spin forever and its spin axis will always point in the same direction. But if there is a torque acting on the system, then it starts to do this. Can you see that the spin axis is revolving? And so we call that precession. And you can do that with a top. So if you want to watch that little video there on tops. So I would like for you to know what is precession and then what causes precession. Okay. So let's take a break, and when we come back, let's talk about energy.